This video is a review for Unit 6. First, let's talk about the trig graphs. You can see that sine and cosine are shown here. What these x and y coordinates represent, if you think about the unit circle, is the cycle as you go around the unit circle where your relative values are. So this right here is a complete cycle. That distance from left to right we call a period. And you see that the period here is 2 pi. And the same thing is true for cosine. Some other things to note, you'll notice that sine starts here at 0, and cosine starts here at 1. Another vocabulary term is amplitude. And you can see here that the max minus the min is the amplitude, divided by 2. So here we have 1 minus -1 divided by 2, and the amplitude is 1. It's always going to be positive because it's distance. And if we have any scalars that we would call vertical stretches in previous units, they're going to increase that amplitude, and the distance from the top to the bottom of this sine curve will increase. If we look at the inverse graphs, cosecant and secant, you'll see that we have some asymptotes now, these vertical lines, because you can't divide by 0. And those show up every pi. And on the cosecant, they start here at 0, and they are every pi. And with the secant, they start at, let's say, pi over 2, and they repeat every pi. So there's a little bit of a shift there. The other thing to note here is that when we had cosine that looked like this, we just flip it upside down. And when cosine was a u, now it's a hill. And this part of the graph is flipped upside down like that. So it's almost, you can see how the inverse comes from this. The same pattern exists over here. If we have a hill, it becomes a u. If we have a u, it becomes a hill. Finally, what else is worth mentioning? This is an even graph and this is an odd graph, meaning that this axis is like a big line of symmetry, and you could fold the graph over to the other side and it's a perfect mirror image. That's why the cosine of pi over 2 is the same as the cosine of negative pi over 2. Or the cosine of pi is the same value as negative pi. We just saw that in table form, but sometimes it helps to make the connection to see it visually. Compare that with an odd function, and what you have to do is take this curve and rotate it around, because it is symmetric with respect to the origin. So if you do that, you'll see that it's the mirror image on the other side, but you'll also see that sine of pi over 2 is 1, and over here it's -1. So in other words, it's the opposite. And if something was on the bottom here at 3 pi over 2, it's on the top at -3 pi over 2. So that's that connection between even and odd functions. If we go down to tangent, you'll see that there are more asymptotes. Remember that tangent is sine over cos, so we can see that wherever cosine is 0, there's the asymptotes. And it flips on the other side, because now we have cosine over sine for cotangent. And our asymptotes are where sine is 0. Also notice the period is shorter. So the entire periodic cycle only takes 1 pi instead of 2 pi like the cosine and sine graphs. Another thing to note, here with tangent we start at 0, and with cotangent we're starting up at approaching infinity, and our 0 is a little bit shifted over. In general, we use this formula for any of the functions that are like a sine function. Y is equal to a sine times bx minus c. Our amplitude comes from this a value. Our period comes from taking the period of the graph, which for sine is 2 pi, and dividing it by our b value. And our phase shift is c divided by b. Normally c would just be our horizontal translation. And if there isn't one, then our phase shift is just going to be 0. But if we are moving left or right, we also have to take into consideration the potential for a horizontal shrink or stretch, because that affects how much we actually move. So that's why PS stands for phase shift. It's the ratio of C over B. Now keep in mind that you're taking the opposite for C. So if it's BX minus 7, then C is 7. And if it's BX plus 7, then C is -7. So for this particular function, we see that the first part here is a vertical translation down 2. This is a vertical stretch. That's our amplitude 3. And this part here, the 20 pi going in front of that, is a horizontal shrink, and it's a huge one actually. And if we consider that for our period, 2 pi divided by our b value, 20 pi, this whole cycle, which originally took 2 pi, is going to finish 1 over 10. So you'll finish a whole lot of cycles before you ever finish one of the original. And our phase shift is c over b. And since there is no c value, it's just 0. We start at the same place. It's just that cycles happen far, far quicker. And there's a vertical stretch, and they're moved down. Next up, if we look at our 4 there, that's a vertical stretch. This is a horizontal shrink. This is a left horizontal translation. So if we consider our amplitude, that's here, 4. Our period, we take 2 pi divided by our b value, which is 3 over 2, and this gives us our new period. The entire cycle completes in 4/3 pi. Our phase shift, we take c over b. And remember, for c, we take the opposite. So if it was plus 9 pi over 4, we're going to do minus 9 pi over 4. And instead of dividing by 3/2, it's a lot easier to multiply by 2/3. You get the same thing, and there's our phase shift. To consider the left and right ends of a trig function, you have to consider where they would be originally. And for the sine graph, they're going to be at 0 and at 2 pi. So one way to do that is to take the original 0 and set it equal to everything inside the parentheses here. So I took 2 pi x minus 4 pi equals 0. And then for my right endpoint, I did the same thing, 2 pi x minus 4 pi equals 2 pi. And if you solve for x, you find your new endpoints. And if you graph it, it looks kind of like this. We have a vertical stretch of 2, and we're moving up 1. So that's why our highest point is at 3, our lowest point is at -1, and here are the starting points, which we calculated using this. Kind of a goofy graph to use for this one, but one thing you could do is you could consider the amplitude first. So keep in mind that this would normally be from 1 to 1, but it's at 1.5 to -1.5, so that's where I get this as an amplitude. And normally this would complete the entire cycle over here at 2 pi, but it completes before that. So there's a horizontal shrink. What I did is I just did a guess and check to figure out what that horizontal shrink ought to be, and I came up with pi over 2. 1.5 was really close, but that one was a little bit more accurate. How do you know which graph? Well, cosine starts at 1, so that tells me that we're looking at the cosine graph and not the sine graph. And this would be my entire function. This graph is a little bit easier. The only thing that changed is the amplitude. And notice that this is the sine graph because we're starting at 0. So keeping in mind the period, 3 pi, I'm going to use this formula to figure out my b value. If the amplitude is -2, well, technically your amplitude is really going to be positive, but that's just telling us that there's a reflection happening here. And then our phase shift, we're going to use the c over b formula. And we can plug into that what we just calculated for b, and then we can use that to solve for c. And we put it all together, and here's our new function. Y is equal to -2 cosine of 2/3 x minus pi. For this next one, our amplitude, -4, goes right in there. And since our period is pi over 2, we're going to use 2 pi over b to solve for b. And now that we have b, we'll plug that in, and we'll use c over b to figure out what our phase shift is. I'm sorry, to figure out what our c value is. They give you the phase shift. And so now that we have c, we plug a, b, and c into the equation, and here you go. For this next one, consider that our period for tangent is pi divided by b. So our b value is 2, so that tells us our period is pi over 2. The amplitude comes from right there in the graph, that's just 3. And to figure out our phase shift, we know that it's c over b, and we just found out what b is, so we can set the phase shift as c over b, and our c value is going to be right here. So that's how we calculate the phase shift, which gives us -3 pi. Our amplitude is 2, shows up right there. Because this is cotangent, we use this formula, pi over b. We plug in the 4, that's our b value, and that tells us our period. To find the phase shift, we want c over b. So that's the opposite of what's there. So it's -pi over 2 divided by 4, and this is our phase shift. Think about for tangent where the asymptotes actually are. The left one's at -pi over 2, and the right one's at pi over 2. So I'm going to set that equal to everything inside the parentheses and solve, and I get -13 pi over 4. I do the same thing on the right. I set the right asymptote, which is pi over 2, equal to everything inside the parentheses, and I get negative 11 pi over 4 when I solve for x. Cotangent has a period of pi over 4 here, and we know that the left should be 0 and the right should be pi. The normal period would be pi, but since it's divided by 4, you can't go by that alone though. You have to use the entire thing. So you set 0 equal to 4x plus pi over 2, and your left asymptote is at negative pi over 8. If you set pi equal to 4x plus pi over 2, you get your right asymptote at pi over 8. That's because of that 4, which is creating this horizontal shrink. Here, I know that for the secant graph, those are my typical left and right, and I can set those equal to everything inside the parentheses, 3 pi x plus 9 pi, and if I solve, my left is here, and my right is here. For the right, I use 3 pi over 2. That's going back to this graph here, and figuring out this is where the cycle begins, this is where the cycle ends. If I do the same thing with cosecant, I start at 0 and I end at 2 pi. Those are my endpoints. So I plug those in and I get negative 1 to 5. 4.7, to evaluate these into degrees, I'm going to take the sine of theta is equal to negative root 3 over 2, which means in my calculator I can press the inverse sine of negative root 3 over 2. There is a negative there, sorry, it's hard to see. And whatever you get, that'll be the answer. I did not actually finish that part, sorry. Same thing here, tangent theta is 2.5, tangent inverse at 2.5 would be your answer. And for this one, secant theta is negative 3.57. So if you flip it, cosine theta is 1 over negative 3.57. So you take the cosine inverse of 1 over negative 3.57. For this one, if I think about where theta is, I'm going to use the tangent ratio. So tangent of theta is x plus 1 over 10. If I want to find out what theta actually is, I can take the inverse tangent of all of that, which is the same thing as saying arctan of x plus 1 over 10. Similar here, if I start with this, I know that I have opposite over hypotenuse, so sine ratio is good to use. That's the same thing. To find the angle, I use the sine inverse, which can also be written as arcsine of x plus 2 over 5. If I want to find exact values, I start by representing cosine of theta as 4 over 7, which is adjacent over hypotenuse. So I stick theta in the corner here and 4 over 7. To find my other leg, I can use the Pythagorean theorem. Remember, it's the square root of the hypotenuse squared minus the other leg squared, so that's root 33, which would mean that sine, opposite over hypotenuse, would be root 33 over 7. But since we want the inverse, it's 7 over root 33. For this next one, sine theta is negative root 2 over 2, which is opposite over hypotenuse. And if we're treating the hypotenuse as 2 and one of these legs is negative root 2, we get some negative things going on, which means it's telling us where we're at, which quadrant. But let's ignore that and just know that if the other one's negative, it'll work out. So we can say that cosine of theta is adjacent over hypotenuse and flip it for secant so that we have negative 2 over root 2. If I wanted to rationalize it, I could. You'd end up with negative 2 root 2 over 2 or negative root 2. Seems worth it in this case to rationalize. Next up, given this ratio, tangent of theta is 2x over root 2. I put theta there, and I have 2x over root 2. To figure out my hypotenuse, that's the square root of this side squared, which will give me 2, plus this side squared, which would give me 4x squared, because 2 squared is 4, x squared is x squared. And if I want to find the cotangent, I have to think about that opposite over adjacent and flip it. So actually, you don't need this. Whoops. Just do this. If I look at cosine as 3x over 4, that's adjacent over hypotenuse, 3x and 4. So this is the square root of the hypotenuse squared minus the leg squared, which gives me the square root of 16 minus 9x squared. So if I use tangent, I have to use opposite over adjacent, and it's going to look like that. Since there's x involved, I just leave it as an algebraic expression, and I walk away. So for all of these, we're treating our triangle here like this. C is the hypotenuse, and big C is the 90-degree angle, and then little a, and then angle A, and little b, and then angle B. So it's across from that is the same letter. So I initially had this set up a little backwards, didn't follow that own policy, but B and B, big A and side A, and this is little c and big C. So if I want to solve all of them, I can figure out the other missing angle by taking 90 minus 6.9, and that'll give me that angle. If I want to find B, I can take the tangent of 6.9 as opposite over adjacent. And if I multiply by 22.5, I can find out what B is. And now that I have B, and that I have my original A, I can take the square root of those squared and add it together to figure out C. For this next one, if you set up big A angle here, 32 degrees, across from that little a side length, big angle B across from that little side length B, and side length C being 11, you can use cosine of 32 is B over 11. So little b is 11 cosine 32. To find out what A is, you're going to take the square root of 11 squared minus B squared, which we just found. And if you want to find the angle B, that's going to be 90 minus 32, and you get your answer. So this being an isosceles triangle, that means the two base angles are the same, this one, and they're both 29, which means if we split it down the middle, we have a 90 degree here, and we can figure out that this one is a total of 122, meaning half of it is 61, because all three of the angles of the big triangle have to add up to 180, and these two are complementary. We can also think of this base, which was originally 19, cut in half as 19 over 2. So if we think of A, little a, as our height, then we can take the tangent of 29 is equal to the altitude divided by 19 halves. Or 19 halves times tangent 29 is equal to the altitude. So you got to get the diagram right. 26 above the horizon, length of shadow, height of 70, tangent 26 is equal to 70 over A. When A is on the bottom, you just kind of switcheroo. So these two switcheroo. What you're actually doing is multiplying by A, then dividing by tangent 26. But think of it that way if you like. It's a nice little shortcut. Now we have a boat and a lighthouse. You're going to have to do some imagination on the lighthouse part. Yep. But anyway, we have an angle of elevation, 1.5 degrees. And then we have the height of the lighthouse. They want to know how far away. So we can use the tangent ratio again. And then for the next one, we have a separate triangle with a larger angle of elevation, which means we're closer, by the way. As you get closer, that angle is going to increase. So to figure out the actual difference, you can take the answer to this one minus the answer to this one, and the difference is how far away the boats are from each other.